Okay, so good morning. As I stated, I'm going to go ahead and go over some of the notes for 2D today. We're going to actually be finishing up 2D tomorrow. Hopefully everybody, did their reading like they were supposed to. And we'll be watching this video that goes with it. I will be doing a Google Meet, so if you have questions on assignments, I'll be able to help you then. And if you're stuck on anything that I explained in this video or any of the reading, I can always go back and answer questions on that too. Okay, so this last section in this unit, because we've been dealing with linear regression, right? This deals with things that can cause issues with your data, right? Like high leverage points and influential points and outliers and things like that, which we did talk a little bit about in 2C. And it goes into more detail as far as what will happen when you deal with them. But the biggest part of this unit is dealing with data that's not linear, right? Because we can only get that R value that we want, right? That strong positive regression value and all, or a strong negative, whatever it is. We can only deal with that if it's linear, right? Even if we do a quadratic regression in our calculator, or even on Desmos, and it gives us an R value, it doesn't mean anything because that R value only applies to linear, right? So sometimes we want to take data that is not linear, right, and make it linear so that we can actually make predictions on it and do all that stuff that we would do with a normal linear regression. And that's the biggest part of this part of the unit. Okay, so basically, and if you've read the section like you're supposed to, what are we going to do to data that's not linear? Well, we're going to linearize it by operations. We're going to be squaring, square rooting, taking the log, raising things to powers. If it's an exponential decay, and you should have learned back in Algebra 2, how do you undo an exponential? You use a log, whether it's log base 10 or ln natural log. But we will be doing all those things to one and sometimes both of the x and the y variables just to see if we can make the data become linear, okay? So power models are anything that has, an exponent on its variable, and that's how we're going to deal with it. And I pretty much already answered the question for number 3. No, we don't just have to change the response variable. We can change one or the other or both. Okay. So same thing when we're transforming the data and we run the linear regression again, we need to make sure we are including what operation we use to make the data linear. And again, you're not going to be expected to do this from scratch, right? You're going to be given data, you're going to be shown it's not linear, and then you're going to be given like how they transformed it and the computer output like we've been dealing with. The biggest change is how you write the regression equation. You have to include what operations they did on the variables when you write it. And we're going to do some examples of that today. Biggest thing on open response questions that they love to do is they will take nonlinear data and transform it like 3 different ways and then have you pick which one is better and then have you justify why it's better. Okay, and so we've talked about how to justify something being linear or being a good fit, and it's still about the residual plot, right? So your residual plot, like before, has to be what? It has to be no curves or patterns. And the data has to be randomly and evenly distributed. Right? And being that they're also going to probably be giving you the computer output stuff for each one of the transformations, you can also say something about the R value, right? You can actually talk about R value as far as which one is strongest. Okay. And they will also, again, give you the new scatter plot of the transformed data. So you'll be talking about all of that when you're talking about why their transformation is working. But let's go ahead and practice a couple of transformations. Then I'll give you a couple of problems to work on today. And that's it. Like I said, we're going to finish up this section tomorrow. Okay, so again, we're going to be writing a regression equation just like before. This is why it's so important to, when you write the equation, to write your variables as words. It's much easier to talk about the transforming that way. Okay, so all the fluff, basically, we're looking at oil spills, and they're talking about how estimating the volume from the radius, which is not really surprising. I mean, how else would you find the volume of something, other than based on the radius if it's something that's circular? Okay, so the data plot or the scatter plot of the original data, you can tell that it is curved. It's not a lot, but it's there. Okay, so it looks more like it might be exponential maybe, or quadratic or whatever. And they're going to be doing several different transformations, or we will be doing several with this data just to show. Okay, so we're going to treat it, and again, this is all the floof that they basically come up with. Basically what they finally decided to do was volume versus radius squared. Even though technically volume is a cubic function, and it would be volume versus radius cubed, they said that the height was constant, which is not really surprising. I believe most oil spills are usually no more than about 6 inches deep, I think. So it's more like, I guess, a cylinder rather than a sphere. But anyway, they decided to go ahead and just do volume versus radius squared. And as you can see, very, very linear at that point, okay? So, and notice, like I told you all on the graphs about making sure you're putting your titles and your units and all that stuff, they have actually showed you what they have done to achieve this. Your volume is still in milliliters, just like it was on the original, but now your radius, which is meters, has been squared, okay? And they're showing you that. All right, so the computer outcome for this, and they even tell you, there's your y equals volume and your x equals radius squared, and you're going to write the least squares regression line in that form. Okay, so remember, y hat a plus bx, y hat being the, please do not forget, predicted y value. That's part of the equation when we write it. That's what that hat means. So if I'm going to write the regression line, what am I predicting? I am predicting volume in milliliters, right? And that's going to equal my y-intercept, which is also always the first one. So negative 0.852 plus my slope, which is always the second one in that first column. Okay, and so what is my x now? My x is now radius squared. So, which is in meters squared. Exactly like they showed it to you on the scatter plot. Okay, so you need to make sure that you are showing that you have transformed the data. That's how we do this. Okay, so not that big a deal as far as writing it, and it's really not that big a deal when you're putting numbers in as far as making predictions. And please note, yes, 2.9 is well within our data set. Even after the squared, it's still well within our data set. 2.9 is, somewhere back here. Okay, so we are going to make a prediction. We're going to use this model that we wrote to make a prediction when the radius is 2.9 meters. All right, so the predicted volume in milliliters is negative 0.852 plus 3.2106 times 2.9 squared, since they are squaring the data. Now I'm going to grab my calculator, plug that in, make sure we're all good. Make sure you grab yours. Okay, so I'm getting negative 0.852 plus 3.2106 times 2.9 squared. My answer, my predicted volume is 26.1491 milliliters. Okay, so again, very straightforward. That point is just algebra is realizing if you squared the variable, then you've got to square it when you're doing a prediction. All right, so now they squared the x, and that made it linear. Well, the next set, they decided they were going to square root the y instead, just to see what that would do. And that also made the data linear. Okay, so y is now the square root of the volume, and the x is now just the radius, the normal radius in meters. Okay, so if we write a computer output, for this, with the y being the volume and the x being the radius, how are we going to write that? Well, again, remember that y hat means predicted. So there's kind of a little shortcut to this one, since we did take the square root of the whole thing. It is the square root of the predicted volume, right, in milliliters, equals negative 0.0891 plus 1.7985 times the radius in meters. Okay, so again, very straightforward. Taking a look specifically at what they did to it, all you have to remember is that you're putting that into the equation when you write it. Now, if I wanted to make a prediction with this one, right? I'm still being given a radius of 2.9 meters. So I want you to keep in mind, again, algebra-wise, what I'm going to have to actually do. So if I do negative 0.0891 plus 1.7985 times 2.9, notice I'm not squaring my radius anymore. Okay, so just substitute that in to start with. Negative 0.0891 plus 2.9. Okay, so that is 5.12655. But remember, please, that is the square root of the predicted volume. So how are you going to now go back and actually try and find the predicted volume? How do you undo a square root? You're going to have to square both sides, right? So that's the little difference when you've got a square root in there. So if you square root that, and I'm just going to go up and select it and hit squared so I don't have to round afterwards. All right, so now my predicted volume is 26.2815 milliliters. Okay, and that's where I'm going to end it for today. And then tomorrow we'll talk about with logs and with all kinds of other stuff. And we'll also get more into the high leverage and points like that to see, you know, how we can describe them when we can remove them or what kind of effect they have, more so than we talked about in 3C. So for today, these are the three problems that I want you to work on, 3, 7, and 8 from pages 223 to 225. And again, I'll be on the Google Meet at normal class time, so hopefully you watch this and have done your reading beforehand. All right, I will see you later.